Okay, in this video we're going to go over the review for the Honors Calculus 4.1 to 4.6, problem numbers 1 to 8. So let's look at the first one, and I see I have to differentiate, and this is an E term. So you're going to have to keep it straight between differentiating E terms and differentiating natural logs. So let's see, I have f prime of x would equal what I see, so I write that down, and then I'm going to multiply the whole thing, I guess down here, times what's the derivative of sine 2x. So you should be saying cosine 2x times 2, so I'm going to say 2 cosine 2x. Okay, so let's write that again down here. I'm going to bring the 7 and the 2 together, so that's going to give me 14. And then why don't I bring up the cosine 2x and then times e to the sine 2x, and we are done. Alright, let's go over to question number 2. And why don't I change ink so that you can just see the difference since they're so close. So f prime of x is going to equal, I'm going to write it down below. Okay, so that looks like I need to do the power rule. So I'm going to say 2 times exactly what is in there, which is tan e to the 3x. Okay, and then times, and I'm going to write it down below again. So times the derivative of tan e to the 3x is going to be secant squared e to the 3x times the derivative of the angle, which is e to the 3x. So that'll be times 3e to the 3x. Okay, let's write this a little bit neater so you can see it. Okay, so starting with the pink over here, that's going to equal, let's see what we can combine. How about if we combine the 6e to the 3x, we'll put that first, and then in no particular order that we need to do, I'm going to say tan e to the 3x, and then secant squared e to the 3x. Alright, so your angles should be the same for every single tan function, so just make sure that you have that. Okay, so let's go on the next page and we'll do problems 3 and 4. Right, looking at question number 3, they want us to take that derivative, so we're going to use the quotient rule. F prime of x equals low, and low is going to be 3x squared plus e2x d high, and d high is going to be negative, and it's going to be sine 3x times 3, so why don't we make it negative 3 sine 3x minus, so far we've done low d high minus high, which is cosine 3x, d low, which is going to be 6x, so that's going to be 6x, and then plus e2x is going to be 2e2x. Okay, so let's bring this together a little bit so we can see it a little bit better. Oh, by the way, don't forget, it's all over 3x squared plus e to the 2x squared. Okay, so just making it look a little nicer. It is dangerous to leave this in here because it looks like it's going to be a subtraction. So always bring that in front. So we have negative 3 sine 3x, and we're multiplying that by the 3x squared plus e to the 2x minus cosine 3x times 6x plus 2e 2x. Just squeezing that in, all over 3x squared plus e to the 2x squared. I can't do anything else with that. So let's leave it be. and I'll do problem number 4 on the next page. Alright, here's problem number 4 all by itself. So looking at this problem, you should, oops, sorry, let me go back and do that. So I'm going to undo what I just did. Okay, go back to my red. Okay, so I'm going to write it a little bit bigger. So it says f of x equals e to the e times pi. Okay, there is no variable in that. So that is a constant. So this whole thing is just a number. And the derivative of a number is 0. Numbers do not change, and since derivative is rate of change, we don't have a rate of change, so we say it is 0. Okay, so let's go back and we're going to do problem number 5 on its own page. Alright, so for problem number 5, it says find the value of x at which the function has a possible relative max or min. So you're looking for the critical value. Then use the second derivative test to determine the nature of the function at these points. So it could be this point, it could be these points. So let's figure this out. We're going to take the first derivative. So I have a quotient, so I'm going to use the quotient rule. So quotient rule is going to give me this. Y prime equals low d high minus high d low over low squared. And I'd recommend doing this for low squared. Because what's going to happen is we're going to be able to cancel. So let's cancel in red. Rule of 3 lets me cancel those 3 terms. So I basically factored it out from the numerator and the denominator and put it over itself, and that becomes just a fancy 1, so they can all go. Alright, so let's continue. So now it looks like y prime equals, so let's see what we have. We have a negative 3 minus 7 minus a minus, very carefully, is a plus 3x all over e to the x. So that equals negative 3 and a negative 7 is a negative 10 plus 3x over e to the x, and that has to equal 0 to get your critical value. So for that to equal 0, the numerator has to be 0, and whatever I use for the x can't make the denominator 0, otherwise it's undefined. So there's no way to make the denominator 0, so we should be fine. So setting my numerator equal to 0, I have negative 10 plus 3x equals 0. So positive 10 equals 3x, and divide both sides by 3. X is going to equal 10/3. That's my critical value. So that's the x they were looking for. Now what we're going to do is we're going to take the second derivative. So we're going to take the cleanest version of our first derivative, which is going to be what I'm boxing out right here. That's y prime. We're going to take that y prime, and we're going to take the second derivative and figure out whether my function, my original function, is concave up or concave down at that place. And then I can make a statement about what kind of spot that is, whether it's a max, a min, or a shelf. So let's do all that on the next page. Alright, so I copied over what y prime equaled. So now let's try to find y prime prime. So maybe I'll change my color, make it a little darker. So y prime prime is going to be low d high minus high d low over low squared. Again, I'm going to go and do my low squared that way. Okay, let's do some canceling or factoring out. This, and this will come in 3 places, so I can take that out. We're going to rewrite what we have. So y prime prime equals 3 minus a minus gives me a plus 10, and minus a plus gives me a minus 3x all over e to the x, so therefore that equals 13 minus 3x over e to the x. So to do the second derivative test, I'm going to evaluate this where x is 10 thirds. So I have 13 minus 3, and we'll plug in the 10 thirds. 10 thirds, okay, over e to the 10 third. So I can see that those 3's will cancel out. So my numerator now is 13 minus 10 over e to the 10 thirds. So that's 3 over e to the 10 thirds. That's going to be a positive number. Since it's a positive number, my original function is concave up at that point, and I have identified a min of the function. So I'd write that out in a sentence. So that should take care of 5. Make sure you can do a problem like 5. Okay, we have 6, 7, and 8 next, and we'll do that on the next pages. Okay, so we are asked to simplify the expression with the natural log. So what you need to remember is that, so let's say we have the first one I'm going to kind of do up here. Natural log of e to the negative 5. What does this equal, or what can this be expressed as? So let's investigate that by saying that has to equal q. So since I'm not sure what it equals, how about if we write it in exponential forms? So what's our base? Our base is e. Logs equal exponents. What's our exponent? Hold on a second. Let me stop for 1 second. Okay, so we're good. So logs equal exponents. That's my exponent, the q, and that has to equal whatever was behind the log term. So I can see that q equals negative 5 by using unique log. So therefore, this just equals negative 5. So what I know I can observe. If I have natural log and e next to each other, I can simplify the expression as the exponent of the e term. Okay, so look at this next one now, number 7, with this newfound knowledge. We could work it through the same way, or we can apply what we just learned. So here I have natural log and e right here next to each other. So that 7 really equals x to the natural log of 2 because that's the power of e, and I proved that up here. So can't I also write this, undoing the power property, as natural log of 2 to the x? So either answer is good. Look at this next one. So here, what I have, so I think I'm going to rewrite e down here. So let's see if I can do that. If I, let's try something fancy here. What if I go like that and I say select? Will that cut? Nope, it will not. Paste. No. Okay, so let me cancel that. Alright, so let me just write it. So if I say, what I'm seeing is that it says natural log of 3x plus the natural log of 4, and that's all in an exponent. So if I have the base written one time, and then I have an exponent, and then I have a plus and another term, wouldn't you say that previously this is what that expression could have been? Times e to the natural log of 4, because had I seen that first, wouldn't I have written the base once and then added the exponents? So now if it's in this form, how can I simplify this? Well, I have e next to natural log. Here's e next to natural log. The first term simplifies to 3x. And the second term, I have e next to ln again, simplifies to 4. So that whole expression simplifies to 12x, and you can convince yourself of that by changing the form to log form and seeing what you're getting. So that last answer is 12x. So this is the end of the video. There are 2 more videos on the rest of this packet.